Hi, everybody. So you should know that I didn't want to give this talk. So I'm seeing people going away from the door right now. It's like, oh, then I can go see something else. I didn't mean to give this talk. I prepared this talk for a different audience. But Olve wrote me email, Olve Maudal, one of the organizers. And he's not here, he doesn't care. But at any rate, so Olve wrote me email and said, we want to talk about comparisons between programming languages and be as controversial as you can. As controversial as you can, not knowing who he's dealing with. And here we go. So I'm going to talk about the most average function there is. The most average function in the world. And please give me red cards only. I only want the red card. I'm going to measure my performance in red cards. So, starting with a simple question, what is a good language for getting work done? When I say work, I mean computation. I mean, actual verifiable computation that does something useful for humankind. And I'm sure each of us has a few ideas about what some criteria would be. And mine are the following. I would like a language that is algorithmically inclined. It makes it easy to take an algorithm from a book and translate it into code. I'm seeing a few nods, thank you very much. I feel better already. I also want a language that keeps it real, and by that I mean acknowledges the realities of the hardware it runs on. Okay, so it's kind of, we don't want to implement algorithms, but we don't want to implement algorithms on an abstract machine. We want to implement them on an actual machine that huffs and puffs and gets hot and dirty and leaks oil and that kind of stuff, right? Number 3 of my criteria is allows you to do what you want to do. This is a bit subtle. I find very interesting. Whenever I find I want to do X, I know it's possible. There's no laws of physics preventing it. Yet my environment does not allow me to do it. That's a red flag, right? You want to be allowed to do what you want to do. And after you've done it, code reads like it does what you want it to do. And that's a test that some languages, such as Perl, don't quite pass. Right? So, there are contests like, what's the longest sequence of random characters that Perl is going to consider a valid program? And that kind of stuff, right? So, you do want to have such a language that you can read because code is more read than written all the time and that kind of stuff. So, no surprise here. Now, just for kicks, I totally agree that your list may be different. You may be looking for different abstractions, different things that matter to you, and that's totally fine. There's no contest there. But because Olve wrote me, I'm the guy with the really loud microphone, so I get to say what I think. Please feel free to interrupt me and say, that's the stupidest thing I've ever heard. So, algorithmically inclined. I can take an algorithm from a math book or write my own, and it's going to translate somewhat naturally into code. And if you do look at any algorithms book, you're going to see that most algorithms entail mutation, or at least many of them. I'm sure you know there's pure functional languages that do not allow mutation, and all of a sudden I have a problem. It's like, well, that means I can't do what I want to do. So I want mutation as an option. Of course, I think the answer of a functional program would be there are ways to allow mutation even within functional context, etc., etc. But prima facie, I can say I want mutation. And I want to have things like arrays, and I want to have referential data structures for lists and trees and hash tables and whatnot. So these are things that you would want to have. Algorithmic inclined. Of course, it's not only algorithms you want to do because there's a lot of second-order issues you need to worry about, such as, you want to maintain your code, you want to eliminate a variety of classes of bugs by doing type checking, even unit testing. You should be able to pass a function to another in a higher-order function manner. So, before long, the list gets quite long, right? to the error handling and stuff. Keeping it real, I think there should be some honest protocol between your language and the machine. A machine is going to have fixed sized numbers. It's going to have fixed size numbers. It's going to have mutation. Memory is going to be mutable, right? It's going to have contiguous, loosely typed arrays because the entire memory is like a large array. So this would be sort of the simplest data structure that is one by one representing a computer. That would be an array. Addresses of things are things. You can load the pointer into a register, and that's a thing, right? It's a word that you get to load and interpret different way than you would interpret an integer. You want layout control. You want to put your data in memory by hand as you wish, right? You want to have control over how data gets placed in memory. And you shouldn't find yourself in the need to rewrite from prototype to production, as it happens with many languages that ignore these realities, right? So, all of a sudden, we're looking here, and, I came in peace. I mean, I don't want to antagonize anybody, but there are languages that, like, first order of business, there's no fixed size numbers. And first of all, there's no arrays. Everything is an associative array or is a list. And this doesn't quite vibe with me. Does it vibe with you? You didn't? I was just saying there are languages that decide from day one they're not going to have fixed-sized integers. They're not going to have contiguous arrays. This, the way we roll on this machine that has fixed-sized integers and arrays is we're going to ignore that. We're not going to accept that at all. Yes, please.
So you say you want to represent other realities honestly, and you say that memory is a contiguous array. But if you look at modern machines, they don't really have that as reality anymore. You have multiple layers of caches that affect how memory is actually accessed. You have massively out-of-order machines that, so the model that we're used to programming against does not really represent modern machines.
So the point was, well, you say memory is contiguous and sort of flat and nice, but actually current machines, they have multiple levels of cache hierarchies, and they have out-of-order execution, right? I would not mind primitives for expressing that within a language. But what machines do with these cache hierarchies and such is they make this model fast. Like, for example, the cache memory, if you have like, let's say, 1 gigabyte of cache memory, that's not going to be added to your capacity. It's just going to be used surreptitiously without even knowing by the machine to emulate for you a contiguous block of memory. Yes? Is that a question? Okay. All right. He's here. Okay. So, that creates issues with ideological languages. An ideological language is one that creates a sweeping, has a sweeping first-order decision that's going to affect the entire design of the rest of the language. For example, everything an object. Because, on a machine, not everything is an object. There are things that are not objects. And this is the way it is. I mean, you can't escape it. So once you claim everything is an object, you lose the ability to represent with fidelity things that are not objects. Everything is a function. Church numerals are the most terrifying thing in the universe. The notion that I can represent a number by just taking the steps from number 0 all the way to that number is, to me, very scary. Everything is a list. What happened to arrays? So let's choose the slowest data structure that works and use that for everything. We make that this is our first business decision. The first order of business, ladies and gentlemen, everybody please in line. We're going to use the list from now on as everything representable in our machine. No, thank you. Everything is immutable. I love functional programming. I love immutability. I love purity. In public, in private time. I love purity. I love these are good principles to live by, and not to live by, to live into, to aspire to, in a way asymptotically if you wish. But to have that as an imposition, to not give me the option, that's a bit of a problem because, the machine does have mutable data. And actually, he made a good point earlier. Actually, the mutation on the machine is a bit tenuous nowadays. Because whenever you mutate, you make that cache dirty, which is already kind of a bad word. You make the cache dirty, and you need to write it back. And there needs to be protocols for ensuring things are maintained, synchronized across threads and all that nonsense. So mutability is already kind of a tenuous proposition in current machines. However, mutability of registers is great, works awesomely, and registers are local. And generally, once in a while, I do want to mutate things. And, everything is somehow, I'm going to let you fill out the blanks. I don't think everything is somehow the appropriate way of thinking of contemporary machine. There are, of course, second-order issues here. We have things like dependency management, famous quote from Uncle Bob. All the techniques in software engineering are have something to do with dependency management. And I thought that's kind of a stupid thing to say. And then a few years later, I thought, yeah, he was right. He was right here, he was right there, he was right there, he was right there. So dependency management is kind of an important topic for us. Debugging, unit testing, maintenance, and all of these higher order issues are good to have in a good language. Who knows about these two fine gentlemen? What did they write famously? The Structure Interpretation of Computer Programs, famous book. And they have a very nice pull-out code. Programs must be written for humans to look at and only incidentally for machines to execute. An anonymous reply to that would be, the fact that you show the same program to the human and the machine is an abomination. It is tragically flawed. It's as if, there's no interface between the language and you as a reader versus the language and the machine through the compiler. It's like you're driving a car, but instead of having like a nice, nice car and it's inside, it's all like uncovered, and you need to kind of hold the engine there, with your hand, and you need to spark the plugs yourself with a lighter, all that kind of stuff. So it's, what the machine uses for running, it presents the same interface to you. That's a bit extreme. However, we have no idea how to do better. People have tried. They've tried graphical programming. It works for up to 15-liners. Programs up to 15 lines we know how to do with graphics. With all the squares and all the squiggles and all the, clouds and all the good things. You can draw, up to 15 lines, it scales perfectly. We tried with business logic, let's write the business rules, nicely in like COBOL. And then we have a program that is like, it works, except that 15 lines of code is representing like 150 lines of COBOL. Right, so that didn't quite work. So people tried a number of things. Microsoft has a project that is aimed at non-programs to write business rules. And it's a kind of a long-going research project. I'm not sure, does anyone know what the status is of that project? All right, I haven't heard of it in a while, so I assume they kind of dropped it. I think I'm going to get hate mail for this. Anyhow, I do think that this is kind of an interesting disconnect between The fact that you are looking at the same code that's going to make up exactly on the substrate, I think it's kind of, there's a problem here. Anyhow, remember doing what you want to do. We want to do things like we want to implement algorithms, and the algorithms may be just a bit different depending on particulars of the machine and whatnot. And we end up implementing, I notice, the same algorithm over and over again. I'm sure many of you have written your own things that do searching, or that do some insertion in something, or that do compute the unique something in somewhere, or that do a lot of classic tasks, yet once again, just because the setup is just a bit different, right? And those of you who worked at more than one company, I'm sure you kind of take your little tool chest, or like your C or C++ code or Python scripts and stuff. You just take them with you. It's not illegal because just a few hundreds, thousands, or millions of lines. It's what's a few million lines of code between friends? You just take your little tool chain and say, I have this little function here that verifies that and does this and that does the other, and it works for me really nice, and it provides for me some nice tools. Otherwise, you just end up writing them yourself. And that's the way the cookie crumbles. So I claim that we are dealing with an elusive form of duplication in our daily life in code that it's so pervasive that we kind of trained ourselves to not even see it anymore. I'm seeing nods. So by means of example, we're going to write together the average function. Literally, like the average function that computes the average of a few numbers. And if you Google for, what is the average of numbers, you add up all the numbers and then divide by how many numbers there are. You can explain that to a 6-year-old. Okay? If you crack open any math book, you're going to find this notation, which is x with a bar, which means average of x's, and that's going to be 1 by n, the summation of all x's. So I have the notion of summation. I'm iterating through things, right? I'm kind of doing a few motions that are my algorithm. It's really simple, right? If you want more complicated, you should go back in time and go in my talk this morning, which was a bit more complicated than this. But here is stuck, right? This is the algorithm we're going to look at. And we want to do a few simple things to make sure we don't screw up a few details. Number one, we should not walk our input twice. Do you agree? Hands up if you agree. We don't want to go once to sum the numbers and once again to count the numbers. Agreed? This is an important point. Thank you. Yes, and thank you. Yes. I'm just saying like that for the camera because nobody's doing anything. Okay, so we want to not, imagine mathematicians don't do this. There's a joke with the mathematician, the physician, and the programmer who have the water and the coffee, and the programmer throws away the water and applies the routine that he has already, which is fill the thing with new water. So not good. A mathematician would laugh at this, would be like, hey, Jack, guess what I spoke to this programmer, and guess how they do average. They go once through the numbers, they add them, and then they go once again and count them, and then they do the operation. So you don't want to do that. It's just goofy. We also want to be generic. And this is sort of where this is our machine part. We want to work with all reasonably applicable types. That means things like small integers, large integers, single precision floating point numbers, double precision large floating point numbers, unlimited precision integers, unlimited precision floating point, unlimited precision real numbers. Numbers that you have not seen yet, that have not been invented yet. You want to be able to compute the average of things that you haven't seen yet. And be recognizable. You want the algorithm to look a bit like this. You don't want to go wildly away from the notion that you're summing some numbers and you're making one division and you're kind of home free. We have agreement on that, ladies and gentlemen? Thank you. So what's the best language in the world? Haskell. So I swear to God, first I chose that, this is not cherry-picked. I chose the function and then I Googled. Haskell average function. It turns out it's a research project. Haskell types, this is kind of copy and paste, so maybe I couldn't even parse the sentence. Haskell types frustrating. Maybe R frustrating or whatever. A simple average function, it seems like the simplest thing in the world, right? Wrong. So this programmer, on Stack Overflow couldn't figure out how to implement the average in Haskell. By the way, Lisp also has, I couldn't find any average function in Lisp that doesn't walk the input twice. It doesn't exist. It's against the unwritten laws of Lisp. You can't write it. If you write, you're going to explode. Okay? It's the law. I didn't make the rules. In Haskell, however, it can, but it's just difficult. So finally, there's discussion, Stack Overflow, people kind of going up and down and whatever, and they say, well, here's the thing. You say average axis equals real to fraction sum x's divided by generic length x's. Well, that's kind of who knows what the difference between generic length and length is? Maybe that's the wrong audience. But generic length is able to compute the length of a list of integrals and a list of floating point numbers or rational numbers or whatever. So it's generic in two things. So it can express with the same code the average of rational numbers and integers. Cool. So I have this real to frac. Very nice. However, the problem is it walks the input twice. So it still walks the input twice, even though it looks already kind of elaborate. Fine. Any ideas on how to improve that? Yes, please.
You make an inner function where you accumulate the sum and you accumulate the count.
You make it a function where you accumulate the sum and you accumulate the count simultaneously, and in the end you have both, right? In my case, I have a slightly different solution, just a bit. I Googled again. I go Haskell average function walks the input just once, or something like that. I even forgot. And that took us to this solution. Of course, the X-bank patterns, good friend. Of course you gotta use that, it's obvious. I did not write this code, and this is not a joke. This is a serious, it's actually a blog post. It's a blog post on how to write the average function in Haskell. It's part of a series of blog posts on how to write the average function in Haskell. I am not kidding. I think it does what he said it does. You walk the list, you accumulate things, because I can see here you sum a plus b and you sum c plus 1 because you want to accumulate the guy like an idiot. And then you apply to 0, 0, and through some magic happens, and boom, you got it. Yay. All right. Well, I gotta give it to Haskell. It looks almost exactly like this. It looks like amazingly similar. I look at this. I can't tell the difference. It's just the font. That's it. There's no substantive difference here that I can. Man, I'm going to get hate mail for that. I'm going to be destroyed. All right. So let's take a look at the implementation in the deep programming language. And it's a simple, modest function that says average sequence, and it does a loop, and pretty much what you'd expect. There's this notation. So for those of you who use C++, this is this way of writing. This is a template function templatized by SEQ, right? Sequence. So this means this is a generic parameter, and this is a regular parameter to the function. So I'm going to have a sequence of anything, and I'm going to sum them up. And of course, for this to work, the the sum must be addable from x and must be divisible by x's.length and stuff like that. This is a mother star because it doesn't satisfy many of our requirements. For example, it doesn't work with anything that's summable. Let's fix that. Just to preempt a possible protest, people say recursion is better. And recursion, in this case, does not work. You must do non-tail recursion. Non-tail recursion means it's going to consume linear heap, linear stack in the size of the input. Right? If you say here sum plus equal average of x's without the first element, right? So that would be the recursive solution, which is taught in all functional programming courses. And that's actually not tail recursive, which means it it violates an important law of whatever, which is, well, we don't want a function that consumes linear memory just to compute something that should be done in constant space. I find it quite interesting that I was at the university taking classes, and in one class, they literally, like at 10 a.m., we teach us complexity, and constant space is better than linear space and whatever, polynomial space, and so there's this hierarchy of p spaces and whatnot, right? And then you're like, okay, fine, wow, that's cool. So we want constant space. All the algorithms that matter should be done in as little space as possible. And then 10 minutes break, and then there's a functional programming course. Yeah, space, we don't care. Yeah, this is not something we do. So I find this quite hypocritical. But there is a version that does not require linear stack space. It's a function that defines a function inside as an accumulator. And just because it could have any name, I called it Hitler. You can tell my feelings about this approach. So the way Hitler works is you pass it the seed of computation. This would be my sum, and this would be my count. And it's going to invoke itself recursively in a tail manner, and then we're kind of nicely done, right? Actually, I forgot to divide here and something. Oh yeah, no, it's okay. So anyway, this kind of approach is not something that I would condone, definitely not. And again, it doesn't look like anything close to the nice math formula, which does one iteration and is done. Fine. How about this? Recurrence. It doesn't take a Ramanujan to write this formula, which is computes the average of n plus 1 numbers, given the average of n numbers, and the next number. Agreed? Think it over. It takes a few seconds because this an would be the average of the previous numbers, and you multiply by n, the n goes away. So you have all of the numbers summed, and then divide by n plus 1, you get the average of n plus 1. What's the trouble with this function? What's the trouble with this recurrence formula, please? You're going to lose precision. I love it because it's not on the slide. So you risk to accumulate errors because you do a bunch of multiplications and divisions, and you're going to slowly go insane, right? It's like you eat a bit of lead every day, right? You get slowly kind of insane, right? What are the disadvantages? It's on the slide. For every, to get to the average of n numbers, you're going to have to do n multiplications, n divisions, and 2n additions. No, thank you. By means of raised hands, who agrees that this is not an effective way to do things? Thank you very much. I call unanimity, except for the people who are sleeping. However, people do this. I found it done in a public library of a programming language, standard library of a programming language. And when I pointed that out, I was destroyed. Enter Reddit. Please help me define the most average function there is. So I posted this on the Rust Reddit group. I love Rust, don't get me wrong. I love it, great marketing, I love it. So I wrote pretty much what I told you. How do you go about this, and et cetera, et cetera. Well, I didn't get a lot of votes. All right. And then I was, I don't have my glasses, so there we go. All right, so here's what I write. When I discovered, so this is actually in the Rust standard library. Top line. Do you guys see from the back? Paul, can you see? Okay. Let me make just a bit bigger. So I found this in the Rust standard library. It has a statistics package, which is, professionally written. It's kind of a thing. And I said, sorry. Ugh. And I wrote, that's a terrible way of computing the mean of anything. Grossly inefficient and marred by accumulating errors. So bad, in fact, I omitted it from a review of solutions I found on the net in a recent talk. A better way to go would be to keep the accumulated sum and do the division upon the mean being requested. Of course, the right formula I want here, the right recurrence is with the sum. You keep the sum as a running recurrence, and whenever you ask for the average, of course, I'm giving you the sum divided by the number. So you do only one division when asked. Like as things go, like right now, you do a division per each iteration. So I don't know, is this foul language? Who thinks this is offensive? I mean, I'm a bit insecure right now because here's what happened. First of all, my post got minus 18 points, which is kind of a negative record. And then, ask someone, I see a bunch of downvotes, I ask, which parts of what I wrote were uncool by community standards, thanks. Well, I will happily downvote people who I think are obnoxious. The problem is I touched the sacred cow. The moment you criticize the standard library of the Rust programming language, you're going to have a bad day. And so I did. I was essentially like, oh, there's nothing significant in this thread except that I was laughed out the door. Nobody even understood what I wanted to do. Nobody cared. I didn't get any advice. I didn't get any light. I did get a lot of heat, though. All right, so now let's actually do the right thing and look at a few problems that kind of take us from the nice algorithms world into the concrete bits and pieces world. Well, first of all, how do you deal with averaging integrals? Consider this: you have an image, and you want to compute the average pixel, whatever intensity, color, whatnot, and you're averaging 8-bit numbers. How would you go about it? What types do you use for your summation and what types do you use for your division? So we're starting with unsigned car. Yes, please. Double or float. Do you want to sum using double or float, or divide using double or float, or both? Well, the summation in double is a bit more expensive than summation in long integers. So maybe I want to do something like this. I sum the bytes in a long integer because that's one cycle per iteration. And then when I do the division, I definitely don't want to do the integral division because I don't the average pixel is 8. right? I want the fractional number. I want the full information. So I do the division in double. So all of a sudden, we're encountering this complicated world in which integrals must be summed in another integral type, but different than the original integral potentially, and the division should occur in kind of some fractional type, right? So this is the right way to average integrals. I don't think you want to average integrals and truncate like, like an idiot in the last step. Yeah, of course, I'm going to throw away all of this information. I don't care. No, you do want the information. Otherwise, you sum by hand, right? Then we have things like custom numerics, big integer. Yeah, this doesn't. Okay, I thought this is fancy, really, but it's big integer, things like infinite precision, reals, and all that stuff. And worst of all, there are sequences of which I don't know the length in advance. There's singly linked lists, there's filters on other sequences, there are file streams, etc. Anything that comes as a stream, you don't know the length in advance, right? However, there are things that you know the length in advance of. And for those, you don't want to do this extra work of plus, 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 right? You don't want to do all these additions because they take time. So all of a sudden, we're looking at two classes of algorithms. We have summation of things that are countable, that I know the size of, and I'm looking at summation of things that I don't know the size of in advance, so I need to keep a track of it myself. So remember I mentioned in the very beginning, there's a subtle form of duplication that we trained ourselves to ignore. There is, and this is it. It's a manifestation of it, right? Another thing is all real numerics should use their own element type for sum and division. Everything that's floating point or whatever, infinite precision, real, you name it, should use its own element type for summation and division. All built-in signed integrals should carry their sum as long or u long for efficiency. As I said, it would be silly to sum all bytes in a byte, but division goes as double. And all custom integrals should carry the sum as their own type, but divide to double. This is contentious. Maybe it's not the best decision, but I couldn't find a better one. So with these two slides, this guy and the previous guy, we are having a specification that we need to implement. So we are looking at, I don't know, let's say maybe 30 lines of specification, right? So you should, whenever the type is a small integer, put in a long. Whenever it's a small integer that's unsigned, put in an unsigned long. Divide by double if it's custom, whatever. So we have a number of decisions that inform our simple loop here. So let's proceed and implement that specification. And in the D language, it turns out it's simple to express what we want to do. So first of all, like alias would be, I'm defining this name to supplant this guy. So we alias E to be the element type of the sequence. If it's an array of doubles, that would be double. If it's an array of integers, that would be int, and so on. So E would be my element type. Now I'm going to do something interesting. I do a query on the capability of type E. Static if is type of E of 0.0. What do you think this guy does? Yes, please.
You construct a numerical zero of the type of your container, check what that type is, or even if it is anything, I guess.
Thank you, exactly. So this is a capability test. I'm trying to initialize an object of type E with the constant 0.0, which is a floating point constant. If that works, the result is going to have a valid type, i.e. E. And the static if queries whether that type exists, whether the expression is correct and compilable. If E is an int, in the D language, you cannot initialize an int from a floating point value. You cannot. And you shouldn't. It shouldn't be in C even, but that's side story, right? So you can't say a floating point number and cram it into an integer. It doesn't fit. Sense and sensibility. So therefore, if E is int and you're trying to create an int from 0.0, it's just not going to work. So the static if is going to return false. Which means here I have all of my fractional types. User-defined, built-in, double float, 80-bit double, unlimited precision real number, you name it. If I can initialize it from a floating point number, it's a floating point number. Okay? In that case, I'm going to say this my summation type is going to be exactly the element, and I'm calling unqualify on it because I don't want it to be like immutable or constant, or I just want it to be mutable. So I'm unqualifying the type. I'm removing the potential qualifiers that would prevent me from changing it. And this is the division type that is going to be the exact same element. Otherwise, so this is all of my fractional numbers, everything that's real. Well, the second capability test, are you an integral type? So I'm looking at, by the way, this bank here, the C++ translation would look like that, right? That's not the love sign, it's just angle brackets. I'm sorry to be prosaic here. So whenever it's like bang in the D language, it means it's like a template instantiation, right? So if the type is integral, then we do some more digging because we want to choose signed types versus unsigned types for the summation. And you test, well, is the smallest representable E, is it less than 0? If it's less than 0, that's a number that can be both negative and positive. Otherwise, it's unsigned because unsigned numbers don't have negative, can't represent negative numbers. And finally, the default case I'm going to go with, this must be something user-defined, and I'm going to go with unqual E and double. So this implementation implements the specification that we just talked about, right? What happens here and what happens there. At this point, I have two types. One is S and one is D. S is the summation type, D is the division type. And what's left to do is to proceed with the algorithm. Remember, we had two algorithms. One was for things I know the length of in advance. One was for things I have no idea about the length in advance. In a traditional approach, I would implement the two algorithms separately. I would duplicate the code. In here, we're going to do something much simpler and more compact, which is enum has length equals is type of items dot length. What is this?
If the type items have a number?
Thank you. So it queries whether this expression has a type, i.e. it exists, it's compilable, it type checks, it's correct. So it's essentially, I'm asking, do you have a method called length? And in the D language, the way it goes is if you implement length, you're required to implement it to mean actually the length of a sequence. You could, of course, you could be perverse and implement length to not do that, return a string. What the hell, right? But that would, you can subvert any type system and any introspection system. Yes?
If your linked list container has a .length method that computes the length, but it's slow.
What if the container has a method that's called length, but is slow, it's O(n)? That would be a programmer mistake. That would be their mistake. In the D language, there's a method called walk length, which is O(n). And best effort, so it's O(n) or O(1) if you can, but this is not best effort. This is, if you implement it ever, you must call it, if you implement it ever, it must be O(1). Otherwise, you use walk length. So length means O(1) length, and again, I'm doing a capability test. Well, enum has length equals is this guy, so has length is sort of a compile time Boolean value. Right? It means this guy is telling me during compilation, not at runtime, not dynamically. It's telling me during compilation whether the type I got knows its length or not. So at this point, I'm going to say, okay, sure. So if it has length, then I know the length, so I'm initializing n from items.length. Otherwise, I'm going to initialize it with 0 and I'm going to compute it. And of course, inside the loop, I have another static if because I want to increment it conditionally. Now, the nice thing is that I get to reuse a lot of the other things in this function instead of writing two artifacts that are completely sort of separate, independent, and mostly duplicate. The nice thing is that this does scale. I've looked at many code bases in the D language, starting from the standard library, and there's hedge funds using the D language, and there's networking companies using it. And essentially, like, static if occurs with the same frequency as if, like every 8 lines. Every 8 lines, you make a design decision. Every 8 lines, you fork what you do. You don't fork at runtime. You fork in design space. So this is what I think is really remarkable, that you get this Fourier transform of the if statement, which is in time domain, because if means like I'm going to go through different paths during runtime. With static if, I'm going through different paths. During compilation, I decide to do different things to generate code different ways. So this is going to generate different functions for different types, and it's going to generate the best function for each type. So, there'll be like, there's a lot of aftermath here, like what do we do with empty inputs? We return NaN here. You can handle it outside. So I don't see this as an important problem. Who knows about the Kahan algorithm? Thank you. Okay, the Bloomberg folks, right? You're not at Bloomberg? Okay, the folks who do real math, okay? So these, it turns out that if you sum many doubles, you're going to, consider this. You have some very large numbers, and you have a lot of small numbers. And if you sum increasingly the small numbers, you sum to a very large number, the large number is going to kind of say, oh, this is too small, I'm not going to modify myself. So you're going to get, even though you have a very long tail of small numbers, those are not going to count for the actual average. And so you get this propagating error problem. Fortunately, there are some very clever algorithms, which I recommend you Google for. These are interesting exercises in algorithm design. They cancel the error progressively as they sum numbers. And they're very interesting. And of course, you want to do that for floating point numbers because you get much better results at a small cost in efficiency. So, I have a few second-order insights after we looked at this, this definition here. So what's cool about OOP? You define interfaces and classes, and you override methods to account for the differences between interfaces and classes. Who thinks OOP is awesome? One, yes, yes. One, okay, this is the right audience. You can go. So, OOP has its limitations. I mean, many people thought it's going to be like amazing in the 90s and early 2000s, and then kind of, wait a second, we can't do all these things we want to do with OOP, right? And then we have in C++, in the C++ milieu, we have the generic programming notion, which is like, let's define generic algorithms, we devise data requirements, we specialize across distinct ADTs, and et cetera, et cetera. And it looks like neither of these fundamental approaches is doing the right thing by our, but what we want to do. We want to implement code without duplication that expresses what we want to do. It doesn't seem to cut just right the proverbial pie. And I think what happens is in OOP, we have type information wastage. The type information is thrown away and it's like, just write down virtuals and you're good. Yeah, they're going to be 7 times as slow, but you're good. Who cares? What's 7 times between friends? So, you lose the type information by inheritance and type erasure. Or you can overuse types by doing a lot of type-based metaprogramming, like in C++ circles, you would do a lot of complicated type-based metaprogramming to do actually pretty trivial things that are easy, should be simple, should be trivial. And I think the key to the kingdom here is introspection. You should be able to look at a type while you compile your code and make decisions depending on what that type knows what to do. You can consider a type at the most basic level as an advertisement for what it can do. Who here codes in like Java? Java? JavaScript? Okay. So anyway, in these languages, it's quite common to open a class, look at a class and look at its methods and treat them as capabilities. Oh, this guy knows how to do bark and knows how to do eat, knows how to do meow. So therefore, I can use these methods in a specific manner. So the type is, the methods of a type, the interface of a type is really an advertisement for what the type is able to do. And why not, I ask, why not open the type during compilation, ask the type what it can do, and generate code depending on those? This is what I think is going to be big in the next decade in programming. Introspection, reflection, and static code generation. And I noticed that a lot of programmers consider code size some sort of a measure of their prowess as programmers. Especially like when I began, I remember like to this day, when I wrote my first 1,000 lines of C, it was awesome. It was a single function, by the way. It was just main. Like, oh yeah, I have a main that's 1,000 lines worth. And you feel it's like, oh, so it means it's I'm a good programmer, I wrote a lot of code, it must be that I solved something interesting. And sadly, this kind of stayed with me for a while. So I think that impeded my development as a programmer because actually the amount of code written is cost, is not profit. Like a good manager will ask, what did you implement that feature? Yes. How many lines did that cost you? What was the price of that feature? I mean, yeah, it cost me like 6,000 lines of code. Maybe that's too much. We paid too much for this. Let's scrap it. Loud. And pay extra to scrap. I actually, on GitHub they show you the numbers of lines you add and the numbers the lines you delete. Right? So, I would pay people on the sum of the absolute of the two. It's just like if you add some lines and delete some lines, I'm taking the absolute value of the lines deleted, and I would add it to the lines you added. And it's like actually not. I would put minus in front of the lines added. Put minus on the lines added. Put plus on the lines deleted, and pay people based on that. Awesome concept. Where do we start? Okay, so. I like to count lines because I want every line to count, to be meaningful. So average can average anything averageable. The most average function there is, it has 26 lines of code. 3 lines are support, imports and naming. 13 lines are the design specification, which from the slides it counts to about just as much. 10 lines are time domain sweat of the bro. That's my computation. So 10 lines is the actual effort. And most lines should matter. You should push computation forward. You should make progress in your computation. You should have every line in your code just push the goddamn thing forward. Sadly, I'm seeing code. At one time, I was looking at the red black tree implementation in C++. I had a simple thing. Do they store the Boolean? Do they massage it in a pointer? Or do they store it separately? The red black tree has some pointers, has a Boolean. Some implementations take the Boolean and stick it in the least significant bit of a pointer. You know what I'm talking about? For size, right? For size purposes. So how difficult it can be, you look at the red-black tree implementation in C++, you see whether the Boolean is massaged in there or not. I gave myself 15 minutes. I could not do it. You don't know where work is being done. Crack open Boost, crack open GCC, like the standard library. Crack open anything. It's all good. Oh my goodness. They send you from one. You don't know where things are. You don't know where work is being done. I want work to be visibly done in code, not scaffolding. It's all like scaffolding is this one line in 100. We're A equals A plus 1. You got it. Right? I don't like that. So it's essential that you have all of this kind of making decisions for design and making decisions about computation and pushing the goddamn computation forward. They should go together in harmony. I mentioned this. There's a bunch of use of static if. I think it's the best construct in the deep programming language. And it changes the way you think quite dramatically. Symmetry is a hedge fund in London, and Weka is a networking company, a network storage company in Tel Aviv. So I was curious to look at their code, and they seem to be using static if about as frequently as if itself. You can't see a page of D language code without a design domain decision. This should be the way things should go in all programming languages. What do you think should be filling the ... in there? Most traders in the stock market think in terms of profit and loss. Zen traders think in terms of Bloomberg. Fees. That's brutal. I didn't mean that. So good trader will think in terms of risk. Actually, they're called risk managers. So all they do is risk management. So if something makes much money, less money, you gotta just say, what's my risk here? How much am I risking, and how do I manage that risk? So this is the most important thing in trading in the stock market, is figuring out what your risk is, what your exposure is, and going from there. Beginners tend to think, I'm making so much money, or I'm losing so much money. It's not about the money, it's about the risk. And I would contend that today most programmers think in terms of things like data structures and algorithms, or interfaces and objects, or lists and functions. Pick your language, pick your favorites. Maybe even over ownership, if you're a Rust programmer. I think programmers should be thinking in terms of introspection and computation. I look at types, I figure out what they can do, and I push computation forward using this information that I gain. Don't forget, a good language should be, in my opinion, algorithmically inclined, keeping it real, allows you to do what you want to do, and the code reads like it does do what you want it to do. And your opinion may be different, and that's brilliant. Thank you very much.